good GD&T people? It's been a while since I've made a video. You know how life goes. And I'm sorry if I've kept you waiting, if that's been what's happening. But even as I've been away, it's been exciting to see the video watch hours keep climbing and the new subscribers coming in. Making videos like this isn't easy for me. I probably overdo it and fuss too much about the details, but they are an amazing opportunity for me to get my thoughts and ideas out into the world, which is incredibly rewarding. And I think this series will epitomize that. And that's because I have a big question about GD&T, an issue that seems to come up literally every day of my working life. And I don't get a whole lot of clarity or satisfaction on it when I read the standard. And it seems like almost everyone I work with in the world of part design and drawings seems to have some version of this same question. So after talking these issues over so many times with so many colleagues, I now believe I have the answer to my own question, and I want to share that all with you, okay? The question is hard to summarize. To start talking about it is to open up multiple avenues into different, somewhat advanced GD&T concepts. And it all starts with some of the things the standard tells us about datum features, indicating that datum features are really best when they are the features that actually locate the part in assembly. We'll come back to this slide and these quotes later on. This same section of the standard on datum reference frames introduces this concept of a coordinate system based on mutually perpendicular planes, and how parts have 6 degrees of freedom within this coordinate space. 3 translations, 3 rotations, which we, quote, may constrain using datum references. It explains how to think of datum precedence with primary datums, secondary datums, and tertiary datums. So maybe this is my question. Just because we may constrain a part in 6 degrees of freedom, must we? What if I'm using my part in such a way that there is not a very evident tertiary or even secondary datum feature, by which we mean functional datum features? Are we required in these cases to choose non-functional datum features, features that do not locate the part in assembly, and force them to be datum features? I don't think we have to. I don't think every part and every interface has to have a primary, secondary, and tertiary datum. Far from it. And it isn't just me. A lot of these ideas are things that I have learned from the people who I have worked with and considered the great GD&T minds. Unfortunately, I think the standard has a little bit of a blind spot when it comes to this. Most of the figures, the illustrations, show parts that are constrained in 6 degrees of freedom by datum features. Most of the figures, okay? But not all. There is one carve-out that we're going to talk about in this very video, where the standard specifically allows only 5 DOF constraint. I take really seriously the section on functional datum features. I always find, when I think it through, that when I force some other unimportant feature into being a datum feature, it always causes me problems. It creates abstractions and contradictions. I'll show you some examples of those. I think the standard leaves open the possibility for a really expansive interpretation that I will roll out for you with this series, but then it doesn't quite explicitly provide any explanation or illustration for a lot of this stuff either. So with some of this, I am in what I consider to be uncharted territory, and I need your help to show me where I'm wrong, if I'm wrong. The way I look at it, where the standard holds back a bit, I'm going to surge forward. But it's only because I think it makes sense, it helps clear up contradictions, it simplifies things, and it results in tolerances that more accurately represent the functional requirements of the parts. And so my plan is to take you step by step through my thoughts on all of this. It's going to be a lot. I'm trying to be thorough and detailed, but also focused. So we'll see how I do. Now, everybody who's taken some GD&T training or who has a nice chart on their cubicle wall or their toolbox, they'll know that in the GD&T system, every part must be constrained in 6 degrees of freedom, right? And usually the way it is presented is something like what you see in figure 4-2 of the standard, or something like this, where the idea is, okay, there's one large surface across the bottom. Actually, this one has a relief in it, but the coplanar surfaces have a relatively big footprint. So obviously we're going to call that my primary datum feature, A, and that's a 3 degree of freedom. I say 3 DOF, if that works for you, a 3 DOF constraint. And then look up top. Oh, this rectangle has a long edge. So that's obviously going to be a secondary datum feature, B, a 2 DOF constraint. And then it has this short edge, which is obviously going to be a tertiary datum feature, C, for 1 DOF, the 6th and final degree of freedom of a fully constrained part. And that's going to make it so I can establish these mutually perpendicular planes. And then where those planes intersect, we can say we have these axes, which are the makings of an XYZ coordinate system, a datum reference frame. And so now we can use basic dimensions to locate these screw holes to the datum features and give them a position tolerance within that datum reference frame that we're now calling A primary, B secondary, C tertiary. But then you think back to functional datum features and you say, wait a minute, this isn't how I was really planning to use this part. The long edge and the short edge are not in contact with anything in this assembly. If I imagine this gray thing is just a detail area of a much larger part, there's not actually anything for a mile around in any direction for my blue part to even touch on. So I want those edges, all the edges, all around, to be loose tolerance features. Sure, I need the holes to be located pretty well to each other, but I don't need them necessarily very well located to the edges. And just to prove the point, I can't even tell the difference between one side of this part and the other. I don't even know which corner of this part is that supposedly crucial 000 point, and I don't even care. Then I read in the standard, section 4.8, that I actually need to make this discernible. So I guess one way to do that would be to put a special chamfer up on the upper left corner there. So now we know which edges of a manufactured part are the datum B and the datum C features. It doesn't feel a whole lot less arbitrary though, does it? What's so special about these edges as opposed to the opposite edges? Do I really have to reject this part if it passed inspection in the opposite orientation, but not in this one? What if everything on my manufactured part is nice and symmetrical, but the profile all around the outside is a little heavy or a little light, and now my holes are a little too close or too far from the edges for this 13 thousandths position tolerance? It doesn't seem like that would affect the function of this part at all. So how can I say that these are the functional datum features? Unless their function is to help me stop thinking about this and move on to the next drawing, right? Well, they're not functional datum features. Using them would impose some inaccurate requirements onto this part that we don't really need. And I'll tell you, there has been an illustration like this in every GD&T guide and course materials I've ever seen. But I would say in the engineering world, the interface that this implies, where a part like this is pushed into a corner and bolted down, it's not very common, not a very favored way to locate parts to each other. What they call the functional assembly that's illustrated in figure 4-2 for the part with datum references a lot like this, I just don't see parts that locate this way. And that's not to say we shouldn't use this. It has some merit. But I would say that the reason you see this so much is not because it's very practical, but because it is probably the simplest possible way to illustrate the concept of the datum reference frame. But it is not going to be a big help for most of your parts. And it's probably misleading in a lot of cases. I think more common would be something like this version, a circular version of the blue part you see here. And the standard has multiple illustrations of parts like this. And you can see it's just kind of the base for this subassembly here, which we'll maybe call a clamp pedestal. This one locates into this pocket where it's bolted to the bottom surface. The pocket's close fitting on the outside diameter of the blue part. And then the rotation is constrained with the pin in the slot, which is important to the alignment of the screw holes. So these close tolerance features, the addition of the pin, these must represent design decisions for what we want out of this part. These will provide a lot of constraint for this part, and for the subassembly too. Hopefully these are derived from the requirements of what we need this device to do though, right? It's pretty well locked in, which is, I guess, what we want. Now for this version of the blue part, and for a lot of parts, the datum feature selection can be pretty obvious, at least where it interfaces to the gray plate. We see this also in the standard. It looks a lot like figure 4-5. Hopefully you were shown something like this if you took GD&T training. Maybe you even have this on your wall chart. I know I've had stuff like this on my channel with an interface that looks a lot like this. And if we're thinking about 6DOF constraint, we are right here in our comfort zone. 3DOF primary datum feature, 2DOF secondary datum feature, 1DOF tertiary datum feature. And we could bicker about the small stuff here, but I think most people would correctly identify datum A, B, and C features a lot like this. That datum reference frame, A primary, B secondary at MMB, C tertiary at MMB, kind of comes to life once we use it in a feature control frame, like we do for these 290 diameter screw clearance holes. It's interesting though that when it comes to what I'll call the 1-inch diameter feature over here, we can see the sense in locating it to datum A primary, B secondary, but it doesn't really buy us anything to include the datum C tertiary reference, does it? Because of the rotational symmetry of the part. If you look toward the bottom of this graphic, 4.15 functional datum features, I think this is the intent behind this first bullet quote here, where it says to use only the required datum features in a feature control frame. Datum C is not required to locate the 1-inch diameter feature, so we're not to use it. No problem. But we do need the datum C tertiary in the position tolerance of the screw clearance holes though, don't we? Because the pin and slot are going to work to constrain this interface in rotation. We need to control the location of the holes, not only to datum feature A and datum feature B, but also to datum feature C, the slot here. And then these center lines drawn through the part are also important because they represent two of the planes of our datum reference frame, clearly converging on the center of the part. And we also have a thing called implied 90 degrees, which would support this interpretation that the basic location of the holes is 90 degrees from the slot in both directions, right? Especially because we are establishing and using this datum reference C. Well, how about this? What do we say if it's decided that we don't really need the rotational constraint provided by the pin? Even better, that we don't have to drill and ream the holes anymore, or buy those pins, or press them in. Good riddance. With no more pin, it's pretty hard to justify the slot anymore, so it's going to go too. Now we can all look at this and know that there is a way to make these parts all fit together. This design seems to have a real place in our toolbox. It's something we want to be able to employ. But what we don't have anymore is an obvious tertiary datum feature in the blue part. Aha, a bunch of you will say. What about when we put the screws in? Then it's constrained on the screw clearances. Well, there's going to be a little sub-theme here that our screw holes and screws are better thought of not as locating features, okay? So stick around for that. And you know, there is another possible design here where we get rid of the holes and we have slots. Now, do you believe me that we're not constrained in rotation? I think we definitely also want this design with the slots in our toolbox. We need to be able to do this. So here's the thing, and let's go into this drawing GD&T 00611, where we're back to the holes. This part, this interface on the bottom, does not have a tertiary datum feature, and we should all be just fine with that. You can see I have the same datum A feature, the same datum B feature, and then over here in the screw clearance holes, I reference those. But since there is no feature that constrains the part in rotation, there is no tertiary datum here. It's seen as irrelevant. Well, you say, wouldn't I then have to accept a part that has its holes poorly located to each other like this? Since I'm free in that last rotational constraint, isn't it like anything goes where I place these holes in rotation? Nope, that is not a thing you would have to worry about. If that were possible, it would explode the fundamental concepts of position tolerance. This horizontal center line that goes across the part, it means something. You can't just ignore this. So these holes are related not only to datum reference frame A primary, B secondary, but they are located as a pattern of features to that datum reference frame, and therefore to each other as well. And so to pass or fail manufactured parts, you could have a gauge like this. Now, for those of you who have seen some of my other videos, you'll have heard me say already that these gauges, and I make them purple so you can recognize them, they're meant to represent practically perfect geometry that helps us to interpret some of the GD&T callouts and datum references. Now, it's pretty rare that most of us actually make gauges anymore. And who knows, maybe we should go back to doing more of it. But however you do this inspection, pretty likely open setup on a CMM these days, I would think that you would have to simulate these conditions, okay? So this one would have datum simulators, what the 2018 standard calls true geometric counterparts. A flat surface for datum A. The datum B simulator is made at the MMB size from the drawing callout. And then we have these 276 diameter gauge pin elements representing the virtual condition of the screw holes, which we get by subtracting the 13 thousandths position tolerance from the MMC hole size of 289. The gauge pins fit into holes of that same exact size, and the holes are in the exact basic location as we have depicted on the drawing with our basic dimensions. And that means if we were delivered the manufactured part we were worried about with the uncontrolled rotational positions of the 290 holes, it wouldn't work with this gauge, and it would be considered non-conforming, a fail. And while we're here, I want to point out another interesting thing we can do with this gauge, which is that we can use it to verify the location of the 1-inch diameter feature up on the top side of the part as well. That would require something like this special gauge element, which we make at the virtual condition of 992. That's the 1.002 MMC minus the 10 thousandths upper frame position tolerance, 992. And importantly, this inspection is happening with the 276 diameter pins still in place, what we'll call a simultaneous requirement. We'll be talking about that some more coming up. Okay, so you can see here that even with no tertiary rotational constraint, we can still fully define the tolerances for the features on this part, including rotational control of the 290 holes. And so far, everything I'm telling you is really well supported in the standard. Most of it found in Section 4 on datum reference frames. It's Section 7 in the 2018 standard. I think that path runs through 4.7 and 4.7.1, which get us into this concept of the three mutually perpendicular planes. Once we get that established, we have an origin we can use to dimension features related to that datum reference frame. 4.10.3 tells us how, when we have a cylindrical datum feature, like our datum B on that last drawing, two of those planes intersect on the datum axis. And then 4.10.3.1 through 4.10.3.3 deal very specifically to parts like my drawing GDTG 00611, making it clear that a tertiary datum constraining rotation is not required, illustrated in figure 4-8, which is 7-14 in 2018. Then there is another little nugget you can see in figure 4-8, and you have to skip way ahead to 4.21 to read about it. What you will see is that they want us to put in these little X, Y, and Z arrows. I guess this defines the origin and the mutually perpendicular planes of the datum reference frame and assigns them an orientation, even without the tertiary datum reference. Seems like kind of a way to accomplish that 6DOF constraint and to identify a coordinate system without having to introduce a non-functional tertiary datum feature. I think it's funny when it comes to the arrows that the standard says we may do it if it is considered necessary. Okay. I'm just now learning 2018 in 2025, I know. But 2018 also has several new requirements in this area and seems to make a big effort to align to Y14.41, which would include the application of GD&T to 3D CAD models or to isometric views. That's not really what I'm trying to do here, but I could see how this could help an inspector, especially using a CMM, trying to map out the inspected positions of hole axes in XYZ. In that sense, I like it, but I'm not sure I've ever seen these arrows on a real drawing. I can even see them causing confusion for someone who's never seen them before. Also, I only really know SolidWorks and NX, but I've never seen this as a canned function in a CAD software, and I would be really surprised if anyone provides it. I had to go and sketch all these arrows, fill them all in, hide the dimensions, apply these labels. I can't imagine many of the engineers or drafters I know actually doing all this. They'd probably just skip it, even if they knew this is what was required. Maybe I'm wrong and there's an industry out there where you're always labeling your axes. I don't know. I've never seen it. Possibly we should be doing more of it. And the CAD developers, maybe they should make it easier for us. What I think you should not do, and what I see all too often, is this idea that I'll just pick one of these holes and I'll call it my Datum C feature, which is what we'll get into next. So here we are on drawing GD&T 00620, where we have a call out for the hole on the right, which we've decided to call the Datum C feature. And then there's another call out for the second hole, this one referencing Datum C as tertiary. Now let's all pause to roll our eyes at this second hole call out. All right, this is the idea that there has to be a tertiary datum feature, which parenthetically, again, the standard says explicitly in this case that we don't need. Okay, so far, is this wrong? Not necessarily. This is legit GD&T in the sense that it has a meaning and recognizable interpretation. And that can be illustrated if we go back to the gauges. Now I have a Datum C simulator here, this pin, in addition to the Datum A and Datum B simulators. And then the idea here is that the manufactured part goes on the Datum simulators, and then we check the position of the second screw hole with the gauge element. I guess this is one way to think about it. One thing that's kind of interesting about this is that both the Datum C simulator and the gauge element are the same size, 276, because the holes both have the same virtual condition. It makes you ask, what is so special about one or the other of these holes? Couldn't I place this part on the gauge two different ways? Would it make any difference? Probably I would have to add some kind of marking or special feature somewhere to indicate which of the holes is the Datum C feature. This is a case where I feel like I am indifferent about a datum feature, which for me is an indicator that neither hole is a functional datum feature. But you know what? I think the thing that's going to give people the most pause on this drawing is the two hole callouts for two identical holes. That feels inefficient. I am pretty sure if I submit this drawing, someone is going to ask me, can't this just be a 2x hole callout? Which gives me another example to contemplate in this exhaustive approach, and this is GD&T 00621. Maybe we could go back to one callout and then use the pattern of two holes as a tertiary datum feature. And I'm not sure I've even seen very much of this. What you see more often is for a pattern of screw holes to be used as a secondary datum feature. Also pretty often a bad idea, I think, even though the standard seems to push it. But this part and this interface already has an indisputable secondary datum feature, this close-fitting cylindrical Datum B feature. We're keeping that and now claiming that this pattern of holes is a tertiary datum feature. If we were to follow through on this, it would give us a gauge that now has 2 pins for us to use as a Datum C simulator. This is a little edgy, I think. I mean, now our tertiary datum simulator, supposedly one DOF, only constraining in rotation, is also now at 2 cylindrical features, our most complex datum simulator, compared to 1 cylinder and 1 planar feature. Does that make sense? And if these look complex and constraining, just remember, these holes could also be slots. Are the slots a tertiary datum feature? But let's go back to the drawing again, because I don't think we are even allowed to do this. And that's because we've identified a datum feature C, but then we don't reference datum C anywhere else on the drawing. On GD&T 00620, we used datum C in the position tolerance for the second screw hole, if you remember that. But here, there is no separate call out for the second screw hole. Maybe we could force a datum C tertiary reference into this call out for the 1-inch diameter feature. I should think about it some, but I have my doubts about whether there is a scenario in which that could matter. I want to stick with my interpretation of 4.15, functional datum features, that tells us we should reference only the required datum features. And tertiary rotational constraint is just not required here. And that's kind of the thing with all of these. Whether we have the 2 virtual condition gauge elements, like the illustration up on top here, the 2 datum simulators, like the illustration on the bottom, or one of each, like in the middle. They're all 276 diameter, and they're all functionally identical. This is what we might call a distinction without a difference. The difference is on the drawing, okay? This one is just a lot simpler and doesn't contain the contradictions and problems posed by the drawings that try to force a tertiary datum. I understand why someone would want to force a tertiary datum, but my message to you is that you don't have to. And you actually already know that you don't have to. Let's go back even and look at this drawing, GD&T 00610, which has datum references fully constraining the part in 6 degrees of freedom. This is the one with the notch. The call out for the 290 diameter holes uses all of those datum references. But that's sort of the exception here, isn't it? As we said, the 1-inch diameter feature doesn't use the datum C tertiary. This 257 diameter through hole doesn't have a tertiary datum reference. Even on the notch here, which will become our datum C feature, we don't have a tertiary datum reference. On our datum B feature, we don't even have a secondary datum reference. And it's understood in the cases of the datum features that we are building from one callout up to the next, establishing the datum reference frame. Fine. But in the process, we are dealing with sub-6 DOF constraint all the time. So maybe if you are comfortable with sub-6 DOF and certain callouts, maybe you can get comfortable with an entire part without rotational constraint. Remember, you have full position control of these holes even without the tertiary datum. This is a failed inspection. And again, the standard explicitly says in 4.10.3 that a part like this does not require tertiary rotational constraint, and it provides several examples. We don't benefit at all from forcing there to be a tertiary datum feature on this part. 4.15 also says that the basis for the selection of our datum features is to be the functional requirements of the design. On this one, I will say that the attempt to pull in one or both of the screw holes as a tertiary datum feature is like a good faith effort to create a functional datum reference. But I think I've also shown you that this doesn't really do anything for the functional requirements of the design. We get the same exact function with no tertiary datum reference as we do if we try to force one. So one thing we've learned from these last few examples is that we don't need tertiary rotational constraint for a part like this. That's great and useful, but not exactly life-changing. What's really remarkable about it, I think, is that the standard has now given us at least this one example of a part that has datum features creating constraint in not 6, but 5 degrees of freedom. Well, if a circular part can be fully defined while constrained in only 5 degrees of freedom, can there be other geometries where this applies? So stay tuned for the next episode of this series, where we're going to keep digging until we get to the bottom of this, all right? Until then, this is the GD&T Guy signing out.